Okay, so I welcome you all for today's lab visit talks. And today we have with us Dr. Eli Slenders, from Italian Institute of Technology. And, he's predominantly working in single molecule, microscopy, fluorescence correlation spectroscopy, and related, stuffs, which is at the frontier of science and technology. I'll talk a little bit about Eli's past. So Eli has obtained his bachelor degree in physics from Hasselt University, Belgium, and Master of Science from KU Leuven, Belgium, and PhD in physics from Hasselt University. Since 2019, Eli, is a researcher at Italian Institute of Technology, and he's a Marie Curie Fellow. His current research is basically design and experimental validation of optical microscopy tools such as multi-photon image scanning microscopy and fluorescence correlation spectroscopy. Most importantly, his current focus is on single molecule imaging, and as I understand from the title of the talk, that he's going to talk about a new kind of detector, which is a SPAD array detector. I think I'm telling it right. So
yes.
I will just now hand it over to Eli to really, go ahead. Please, Eli, please take it over.
Thank you very much. I hope you can see the screen and can hear me loud and clear.
Yeah.
Perfect. So thank you very much for giving me the opportunity to present here today. It's really a pleasure to be invited, and I would like to use this opportunity to discuss our recent work on single molecule imaging. So we recently published a paper on some simulations related to single molecule imaging with SPAD array detectors. And currently we are in the phase of validating these theories in our lab. And so it's a really nice moment, I think, to share with you our latest findings. And I would like to start with a quote by the famous French author, Marcel Proust, who wrote in one of his books, "The only true voyage of discovery would be not to visit strange lands, but to possess other eyes." And I think this quote nicely reflects what we are doing in our lab. In our lab, we have many microscopes that you will find also in other labs, such as a confocal microscope or a STAD microscope. But the key difference between our microscopes and most other microscopes is that we look at things with different eyes. In particular, we are using SPAD array detectors, like you mentioned before. And this SPAD array detector is a small array detector that I will discuss in more detail later today. But what is important is that this gives you extra information. And this extra information you can use to make super resolution images or to get more information about dynamics in your sample and so on. So I think this quote nicely reflects how important it is to have the right eyes to answer a scientific question that you have. And I would like to start the voyage today with a brief recap of confocal microscopy. So as you probably all know, in a confocal microscope, you have an excitation laser here depicted in blue that is focused by the objective lens on the sample. And so on the sample, you create this diffraction limited spot of light. And the sample is typically either autofluorescent or it's labeled with fluorescent molecules, and they absorb the laser light and then they emit fluorescence. And the fluorescence is collected again by the objective lens, passes through the dichroic beam splitter because it has a different color, and is then focused by a lens onto the detector after passing through a pinhole. And the reason that you have this pinhole is because you can block in this way out of focus fluorescence. So fluorescence that is produced above or below the focal plane will be blocked by the pinhole. And so what the photodetector sees is only fluorescence coming from a very thin layer in the focal plane. And then what you do to make an image is you use typically galvanometric scan mirrors that move the laser beam in X and Y direction across the sample. And for each position of the laser beam, you measure the intensity of the fluorescence with a photodetector. Here you see it better in this animation. So you have your sample. The laser beam scans the sample, typically in a raster pattern. And for each position of the laser beam, you measure an intensity value with a single element detector, which then is used to create a digital image of your sample. Now, the problem with such a single element detector is that you lose information by spatially integrating the signal. What do I mean by that? Well, when you have a single element detector, you don't have any information about where the photons in the image plane are, because you integrate everything. Everything that passes through the pinhole is detected with a single element detector. So you accumulate all those photons regardless of their position in space. And this is a loss of information. And what you do in image scanning microscopy is to use the spatial information to improve your microscope. So in image scanning microscopy, you remove the pinhole and you replace the single element detector with an array detector. And this can be like 5 by 5 pixels or 7 by 7 pixels. And it's placed in the image plane of your microscope. So where you normally have the confocal pinhole. In this case, you don't have a pinhole anymore, but it's not a problem because the size of the detector is typically around 1 to 1.4 array units, which is roughly the same size that you usually use in a confocal microscope. So what happens now? You have your sample, which you scan with the laser beam, but for every position of the laser beam, you don't have a single intensity value anymore, like you have with a single element detector, but instead you have an array detector. You have a small, you have micro images, small images of 5 by 5 pixels or 7 by 7 pixels of your probed region. And so at the end of the scan, you have a 4-dimensional data set. You have 2 dimensions that reflect the position of the laser beam, in this case, XS and YS, and 2 parameters that reflect the position of the pixel in a detector, XD, YD. So you have a 4-dimensional data set, and you can look at it in 2 ways. You can say, okay, we have a series of micro images, but you can also think of it as we have 25 scanned images, because every pixel of your detector is like a channel of your microscope. And so when you make a scan, at the end of the scan, every pixel has produced an image. So we have 25 images in total. And you can see it better in this animation. So again, you have your sample with a laser beam that scans it. And for each channel of the detector, for each pixel of the detector, you have an image that is registered. And then the question is, of course, at the end, when you have these 25 images, how do you analyze this data set? And to answer that question, we need to have a look at what is the difference between these 25 different images. And the answer is, well, every pixel of your detector has a slightly different point spread function. And if we ignore the boundary effects near the edges of the detector, then the main difference between the different point spread functions is that they are laterally shifted with respect to one another. And this shift is the consequence of the position of the pixel in the image plane. You can see it maybe better. No, this animation isn't working, but all the point spread functions are laterally shifted with respect to one another. And as a consequence, also the images that you collect with the different pixels are shifted with respect to one another. So what you do then in post-processing is very simple. You just undo these shifts so that all the images are basically the same. And then you can simply sum all the images and you end up with one image. Now, this one image is a super resolved image. It has a better resolution than what you would have with a normal confocal microscope. And the reason is the following. Here you see an example of an immunolabeled tubulin network in a cell labeled with ATO 647. And when you image the cell with a closed pinhole in a confocal microscope, and with closed, I mean, let's say around 0.2 array units, then you get an image that has a good resolution, because we know from theory that when you close the pinhole in a confocal microscope, the resolution improves. But the problem is that when you do this, you also block a lot of light. And so the signal to noise ratio is really bad, which is why you typically don't do this in a confocal microscope. Typically in a confocal microscope, you set the pinhole to about 1 to 1.4 array units. And this gives you the advantage that you collect a lot more signals. So the signal to noise ratio is a lot better, but by doing this, you lose resolution. And ISM is actually the best of both worlds. In ISM, every pixel is about 0.2 array units in size. So every pixel produces an image with a good resolution, but the overall size of the detector is still about 1 to 1.4 array units. So the total number of photons that you have is the same as if you have an open pinhole. So in ISM, you have both a good resolution and a good signal to noise ratio. Now, in order to implement ISM in a lab, what you need is an array detector. And our lab was the first one to implement a single photon detector array that was specifically designed for laser scanning microscopy. This happened already several years ago. And here you see an example of such a detector. Every pixel of this detector is a single photon avalanche diode. Here you see some specifics. So this is a 5x5 array detector, so 25 pixels in total. The size is about 1.4 array units, and every pixel acts as an independent single photon avalanche diode. So whenever a photon hits a pixel, it produces, let's say, a logical high voltage in that pixel that you can detect with an FPGA, for example. And this is independent for all the pixels. So you cannot really speak anymore of a frame rate because every pixel acts as an independent detector. And because we now have many pixels, we can use this for subdiffraction spatial sampling of our photons. On top of that, every detector, every pixel is a SPAD, a single photon avalanche diode, which means that we also have a very good temporal resolution, and we can detect every photon with a precision of about 100 picoseconds, which allows us to, at the same time, measure the photophysics, for example, the fluorescence lifetime of our sample. There are some other characteristics of the detector. I will not go in detail into this, but I will quickly summarize the results, let's say. So here in the top graph, you see the photon detection efficiency as a function of the wavelength. And you can see that we have a maximum around the green wavelengths. And then when we move towards the red, the efficiency of the detector decreases. The blue and the red curves are different types of SPAD array detectors that we have in our lab. Also, every pixel has a dark count rate, which is the number of counts that are detected even in the absence of light. And so you want this to be as low as possible, obviously. Typical detectors have a dark count rate of about 100 to 1000 counts per pixel per second. So this is a limitation, but this can be solved by cooling the detector, for example. So this field of SPAD array detector development is a field that is rapidly moving and rapidly improving also. So new detectors with better characteristics come out basically every day, so to speak. And yeah, this is important because right now there is a bit of a discussion on whether or not SPAD array detectors are good enough for single molecule imaging, because for single molecule imaging, you have very low photon count rates. And so it's important to have a high photon detection efficiency and a low dark count rate to get a good signal to noise ratio. But like I said, the dark count rate, you can improve a lot by cooling the detector, and the photon detection efficiency, you can also improve by placing, for example, a micro lens array in front of the detector, because you see here that there is some space in between the different pixels, and this space is dead space. So if a photon hits the space in between the pixels, this photon is not detected. And of course, you don't want this, but this can be solved by placing a micro lens array in front of the detector. So the detectors are becoming better and better every day. And I want to convince you today that they're also good enough already. The current generation is good enough to do a single molecule imaging. So I already talked about confocal microscopy and the story from confocal microscopy to image scanning microscopy, which started in our lab several years ago. And we have several papers on this, as you can see here. So you can do image scanning microscopy with the array detector. You can combine this with measuring the fluorescence lifetime, because I said every pixel has a very good temporal resolution. So you can use this for imaging and at the same time measuring the fluorescence lifetime. But we did a lot more than that. We also implemented this array detector in a stat microscope, and this has the advantage that you can use this, that you can have the same resolution as in a normal stat microscope, but with a lower laser, with a lower stat power, thanks to the ISM reconstruction. So this allows you to have, let's say, a more gentle stat imaging system. We also implemented the combination with 2-photon excitation. This has the advantage that you can use long wavelengths. So you can image deep into thick samples. And we showed that also here, the ISM reconstruction gives you an improved resolution compared to a single element detector. Then more recently, we also did the combination with FCS. So FCS is a technique where you measure the dynamics of your sample. For example, the movement of molecules. And with an array detector, you can extract more information about your sample than with a single element detector. For example, not only can you measure the diffusion coefficient of your molecules, but also the type of diffusion that you have, like free diffusion or anomalous diffusion. And if it is anomalous diffusion, which type of anomalous diffusion. So the array detector gives you a lot of information that you don't have with a single element detector. Then also some other labs have been into this field of array detectors. For example, there is this paper where they did quantum ISM, which makes use of the effect that if you have a pulse laser, then every fluorophore can emit at most 1 photon per laser pulse. So it means that if you observe multiple photons after a laser pulse, it means that you have multiple fluorescent molecules. So, and this extra spatial information, this extra information you can use to improve the resolution even further with another factor of 2. And also the combination with SOFI, with the stochastical optical fluctuation imaging, has been done to improve the resolution further. So this is just to say that this array detector has a lot of applications, not only image scanning microscopy, but more than that. And of course, then the next logical step is, can you also do this for single molecule imaging? And like I said before, there has been a bit of a debate about this because the current generation spot array detectors still suffers a little bit from things like the limited photon detection efficiency and the dark count rate in every pixel. But it's already possible with the current generation to do single molecule imaging. And today I want to show 3 possible techniques, 3 approaches for using a small spot array detector in the context of single molecule imaging. First one is wide field imaging, then single molecule image scanning microscopy, and then ISM flux. So first, wide field imaging. What do I mean by this? In this configuration, you park the laser beam in a given position in the sample, so you don't use the Galvo scan mirrors, and you just collect the signal with the spot array detector. This is the most simple implementation that you can think of, let's say. And we tried to do this on a DNA paint sample. This was a commercially available paint sample where you have 3 binding sites that are about 40 nanometers apart from each other. And so we focused the laser beam on a DNA paint origami, and then we imaged the signal with our spot array detector. And then here you see an example of the intensity time trace. So on the vertical axis, you see the photon counts per time bin for all the pixels combined. And on the horizontal axis, the time. And so you see that we have, let's say, background counts. Then at some point, a molecule, a fluorophore, binds to one of the binding sites, and we get fluorescence emission. Then it unbinds. So we have, again, the dark counts, the background, and so on. And sometimes it happens that we have a bigger peak when 2 fluorophores bind at the same moment in time. This is how it looks like on the array detector. This is an example of a frame where there is no fluorophore bound to the DNA paint. Then the second image here is from the first event when a molecule binds to the DNA paint. And you can clearly see here that the position of the molecule is somewhere around here, near the top left corner of the spot array detector. And this image is for the peak where there are 2 fluorophores that are bound at the same time, which we ignored for the data analysis. So what we did was we only looked at single events, we localized those molecules, and then we reconstructed the image. So the question is, how do you do this? How do you analyze this data set? And what you do in normal, let's say, single molecule imaging like paint or Palm or Storm, is that you fit a Gaussian distribution through your data set. But here we have a very limited number of pixels. We have only 25 pixels. And for example, this pixel was not working very well, so we turned it off. So it means we had only 24 pixels. And the molecule is close to the corner. So fitting a Gaussian through such a data set is not ideal. Instead, what we did was a maximum likelihood analysis, which is a type of analysis where you calculate the likelihood that the molecule is at position RE given the photon counts that you observe. And of course, you don't know what RE is, but you can calculate the likelihood for every potential position of the emitter. And then you can make a likelihood map and you can check where the likelihood is the highest. And that position is then the most likely position for the fluorophore. This is the formula that you can use for that. Capital N is the total number of photons that you observe in an event. Small n is the number of photons in every pixel of the detector. And pi is the probability that a photon arrives in pixel I. So it depends on, let's say, the detection point spread function of every pixel, but also the signal to background ratio. So you can use this formula to calculate how likely it is that the molecule is at position RE for all the possible positions RE. So you get this type of likelihood map. Then you check where this is maximum, and that position is then the most likely position of the fluorophore. So we did this type of analysis on our data set, and this is the result. On the left, you see the cumulative image, so what we call the fingerprint, which is just the sum of all the images that we got. And so it shows again that the molecule or the DNA paint must have been somewhere around here. But then when we do the localization analysis, you can clearly see that we have the 3 spots, excuse me, 3 spots that are about 40 nanometers apart as expected based on the sample. So this technique works very well, but of course it has a very small field of view because the field of view of the detector is just several hundreds of nanometers. And of course it would be nice to increase the field of view to scan bigger samples. And the question is, how do we do that? I already told the answer, basically. You can do scanning. So that's the next step that we did. Instead of having the laser beam parked at a given position, we scanned a small area of about 5 by 5 microns. And then you get images very similar to what you see here. So you see the on-off blinking of the fluorophores, but now in multiple DNA origamis. And here you see the photon count rate as a function of time. So you see again, we have the background and then the blinking events. Then in this case, we did the reconstruction by fitting Gaussians through the data set. And then what you see, what you get is this result. So now we have a much bigger field of view, but the localizations that we get are not that good. Like we don't see anymore the 3 positions on a straight line. And the reason is that we were using here the signal of all the detector elements combined. So we summed the signal of all the elements. And then you don't get such a good precision. So then the next step was to use this extra spatial information that you have with the array detector to do the ISM reconstruction. So what you see now on the left is the sum of all the 25 pixels, excuse me, the sum of all the 25 pixels of your detector. And then on the right, the corresponding ISM reconstruction. So you can do this reconstruction, like I said before. You can do this on every frame of your data set, and then you get a much better defined position of the fluorophores. Because now, excuse me, now you have a standard deviation that is, excuse me, square root of 2 times smaller than before. And so the molecules are much better defined, much better localized, and that gives you a better result. So here you see a comparison of the sum 5 by 5 on the left and the ISM reconstruction on the right. And now you see indeed that you have 3 positions that are on a straight line as expected, but with a bigger field of view compared to if you have the beam just parked. Then the next step is, can we combine this with fluorescence lifetime? And I already said before, yes, this is possible because every pixel of the spot array detector is a single photon avalanche diode with a very good temporal resolution. So you can combine this with fluorescence lifetime. The only difficulty is you have 25 pixels in case of a 5 by 5 array detector, or even 49 pixels in case of a 7 by 7 array detector. And so you need to have a time tagging platform that is able to detect the arrival time of all the photons in all these channels in parallel. And excuse me. And so what we did was we developed what is called the Bright Eyes TTM, which is an open source time tagging module that is used for single photon microscopy. So everything that you need to build this, this time tagging module and to run it, the code and the hardware, the software, everything is available online. So you can build your own time tagging module. And this module allows you to measure the arrival time of every photon with respect to the last laser pulse of up to 49 channels simultaneously with about 30 picoseconds temporal resolution. So this is very useful in our case because we can connect every pixel of the spot detector to one of the channels of the time tagging module, and then we can measure the arrival time of every photon in every pixel of the detector with very good precision. So we did this during the DNA paint measurements, and the results are what you see here. So you have a histogram now for every pixel of your detector. So we have 25 histograms, and these 25 histograms are very similar, but they're not exactly the same because every pixel has a different signal to noise ratio. For example, the pixel close to the center of the detector will collect a lot more photons, and so the histogram of the central pixel, indicated in black here, will be better, let's say, than the histograms closer to the corner elements. But what is important is that you have a histogram for every channel, and so you can use this information to measure the lifetime, for example, by fitting an exponential decay through the curve. And then in this case, you see that we have about 2.5 nanoseconds of temporal lifetime for this DNA origami. So we can do localization microscopy and at the same time also get information about the fluorescence lifetime. And then the question is maybe, can we get an even better localization precision? And the answer is yes. So the next step is what we call ISM flux. And to explain ISM flux in one phrase, you could say ISM flux is min flux with an array detector. So in min flux, what you do is you have a donut-shaped excitation beam that you move in a given pattern that is called a targeted coordinate pattern. So here you have the donut beam in green. You move the donut beam to different positions. Typically, you have, let's say, 3 positions on a circle and then a 4th position in the center of this circle. And you move the donut beam to these 4 positions, which are around a single active fluorophore, here depicted by the green star. Sorry, the yellow star. So what you do then is you measure the number of photons that you have for every position of the donut beam. So for example, for the first position of the donut beam, you excite the fluorophore a little bit, and so you observe almost 13 photons. Then you move the laser beam to the second position, and you see that it will be excited more, and so you collect more photons, in this case, like around 45 photons. Then you move the laser beam to the third position, where you collect fewer photons than to the 4th position, and so on. So at the end of the measurement, you have 4 numbers, 4 photon count numbers, and then you apply a maximum likelihood estimation to get the most likely position of the fluorophore given these photon count numbers. This was the idea of the original min flux technique. There exist several variations on this concept. For example, you can extend it to 3D, or you can use pulse lasers and so on, but the idea is always the same. And so the question is, can we do this with an array detector also? And the answer is yes. So you have, in this case, the donut beam that moves again to the 4 different positions. But now for every position of the donut beam, you don't have a single intensity value, but you have a small micro image of your sample, a 5 by 5 pixel micro image. And so at the end of the measurement, you don't have 4 numbers, but you have 4 micro images. But the idea for the analysis is the same. You do a maximum likelihood analysis. So you check how likely it is that the molecule is at position RE, given the photon counts that you observe. And the photon counts are now not a list of 4 numbers, but a matrix of, for example, 4 rows and 25 columns. So N now is Nij. And P is now Pij, which is the probability that a photon is detected by a specific combination of donut position and pixel in the detector. So it contains information on both the position of the donut and the detection point spread function of your microscope. But the rest is the same. So you have a very similar formula. You calculate the likelihood for every position, every potential position of the fluorophore. You check where this likelihood is maximum, and that position is then the most likely position of the molecule. The question is, what is the advantage of having the array detector compared to a single element detector? And to answer that question, I want to show an example. So let's say that the molecule is here with where the yellow star is, so close to the center of the circle that you scan. In this case, when you calculate the likelihood map, and you do this for a single element detector and for a 5x5 array detector, you get actually very similar results. You see that we have a likelihood map that has a single local maximum. It's very well defined. So both techniques are able to localize the molecule, and both techniques are able to do it with very similar precision. So based on this result, you may say, okay, there is no use in using an array detector. You don't get any benefit. But the situation is completely different when a molecule is farther away from the center of the circle that you scan. For example, let's say that the molecule is here just outside of this circle. Then in this case, ISM flux, so with an array detector, is still able to tell you where the molecule is. You see that the likelihood map still has only one local maximum, a narrow peak, and the local maximum is very close to the actual position of the molecule, very close to the ground truth. On the other hand, for a single element detector, the situation is completely different. Now you have a very broad distribution, and also you see a second local maximum far away from the ground truth. So in this case, a single element detector cannot tell you anymore where the molecule is because you don't have enough information in this case to localize the molecule. And this is a well-known problem in MinFlux. And you can solve this by doing a kind of pre-localization procedure where you make sure that the molecule is inside the circle before you start the actual MinFlux procedure. But this takes photons, takes time. So it's clear that with an array detector, you can skip this pre-localization step, or at least you can, you don't need to be so precise in your pre-localization, because even if the molecule is outside of the circle, you can localize it pretty well. Here you see some more examples of simulations. So what we did was we simulated the position of the molecule for every position that you see here. And then we calculated the likelihood map. And you see that for each position, we have a single local maximum very close to the ground truth. So even pretty far away from the circle that you scan, you can still localize the molecule with good precision. To make this more quantitative, we calculated the Kramer-Rao bound, which is a lower bound on the variance of the maximum likelihood estimator. So it gives you an estimate of the best obtainable localization precision. And we calculated this analytically for molecules near the optical axis. This is the formula that you get. So it's L divided by 2 times the square root of 2n, where L is the diameter of the circle that you scan. So it can be 50 or 100 or 150 nanometers, whatever you choose. And n is the number of photons that you detect. This formula is the very same formula that you also have in conventional MinFlux. But like I said, this is near the optical axis. If we look at positions farther away from the optical axis, then you can clearly see the difference. So what you see here are maps of the Kramer-Rao bound as a function of the position of the molecule. The left column shows it for a single element detector, and on the right column for ISM flux, so with a 5x5 array detector. And every row is a different diameter of the circle that you scan. And you see that close to the center of the circle, in each situation, an array detector and a single element detector give you nearly the same Kramer-Rao bound, so the same localization uncertainty. But when a molecule moves, or when a molecule is farther away from the center of the circle, like here, for example, you see that you have more than 30 nanometers localization precision with a single element detector, while with ISM flux, it's almost the same as near the center of the circle. So with ISM flux, you have a much bigger field of view, so to speak. And you can see this even better when we zoom out a bit. So here you see, again, a map of the Kramer-Rao bound as a function of the position of the emitter. And you see that basically up to the edges of the detector, we get a very good and stable localization uncertainty. And the only reason that near the corners of the detector, the Kramer-Rao bound goes up a lot is because far away from the donut beams, you don't excite the fluorophore anymore. And of course, if you don't excite the fluorophore, you don't get any photons anymore, and you cannot tell where the fluorophore is. But as long as you excite it, you can localize it with very good localization precision if you have an array detector. This is another example. Here you see basically the same data set as on the right, but now in a line plot. So on the vertical axis, we have the localization uncertainty, and on the horizontal axis, the position. So 0 means close to the optical axis or close to the center of the targeted coordinate pattern. And as you move to the right here, you're looking at positions farther away from the center. And you see that with MinFlux and ISM flux, you have the same localization uncertainty very close to the center of the circle. But then with MinFlux, it goes up very quickly, while with an array detector, it remains stable for a very large field of view. And again, here it goes up, but the only reason it goes up a lot is because you don't excite the fluorophore anymore. And of course, if you don't excite it, then you cannot localize it. So this is a theoretical result that we published recently. And now we are in the phase of experimentally validating this theory. So to conclude, I can say that with this array detector, you get extra spatial information, which you can use for many reasons. You can use it for super resolution imaging, for single molecule imaging, for other techniques that I didn't talk about today also. And since it's a fast array detector, you can still combine all of this with, for example, measuring the fluorescence lifetime. The current generation spot array detectors is already sensitive enough for single molecule localization microscopy. You can clearly see the on-off blinking. You can clearly see that the signal to noise ratio is not so bad. But of course, even the current specs, they will improve with newer generations. So we expect that this will be even better in the future. But already with the current generation, you can localize single molecules and measure at the same time also the fluorescence lifetime. And then I showed some simulation results with ISM flux, where you do MinFlux with an array detector. And this shows that you have an improved localization precision over a large field of view in comparison to MinFlux, which means that you don't need a very precise pre-localization procedure that you need in MinFlux. So it's expected to be more convenient to do experimentally. So what's next? Well, next, of course, is the experimental confirmation of ISM flux, which is what we're currently working on, and also other configurations. I didn't talk about today about Rostmin, but Rostmin is also a very promising technique. Basically, what you do in Rostmin is very similar to MinFlux, but instead of moving the donut beam to these 3 positions on a circle and 1 position in the center of the circle, you move the donut beam in a raster pattern. Which is cool because you can use a normal confocal microscope to do this. You only need to replace the Gaussian beam with a donut beam. But other than that, you can use a normal confocal microscope. You scan the donut beam in a raster pattern, and then you localize the molecule this way. So this is also a very promising approach. And also here we expect an improvement with an array detector compared to a single element detector. And then another interesting next step is focus ISM. We recently published a paper in our lab together with Giorgio Tortarolo on focus ISM for background removal. So you see here in these images that you can clearly see where the molecule is, but you have a bit of background. And this background is not only dark counts that the detector has, but it's also actual fluorescence coming from let's say out of focus molecules. And of course, it would be better to remove this background as much as possible. But with an array detector, you can do this because the signal that is coming from the in-focus molecules has a different signature on the detector than the background, than what is out of focus. Because what is in focus has a more narrow distribution on the array detector than what is out of focus. And so the total signal that you observe, the total macro image, is a linear combination of these two. And if you know the signature in focus and out of focus, then you can, let's say, decompose the two, and you can extract the signal and remove the background. And this is very promising also for single molecule localization microscopy, because you see that we still have a bit of background, and it would be nice to to remove this. So this is for sure a next step in our lab. Okay, with that, I would like to thank my PI, Giuseppe Vici-Domini, and all the other group members of the molecular microscopy and spectroscopy group here in IIT in Genoa. Also, our colleagues from Genoa Instruments. Genoa Instruments is a spin-off company of IIT that commercializes the spot array detector. And also, I want to thank our collaborators of Politecnico in Milan, in particular the lab of Alberto Tosi, who helped us with the development of the spot array detector. And then, of course, I would like to thank also the funding agencies, the ERC and the Marie Curie. And I would like to thank you again for inviting me. And I'm happy to take questions. Thank you very much.
Thank you, Ali. It was really nice. Good talk.
Thank you.
I would say a beautiful talk at the frontier of imaging technology. People are doing a lot as far as detectors are concerned. And I think it is not only related to microscopy. It can go to machine learning and all other aspects of I would say this detector can be useful. I just want to ask if anyone has a question that they want to ask. Okay, so I don't see any hands, but Ali, I have something that I want to ask you. How do you think your SPAD detectors compares with EMCCD?
I think one of the main advantages of a SPAD array detector is the speed. So with an EMCCD, you have a good quantum efficiency. They are very sensitive, but they lack the speed. And when you combine it with a laser scanning microscope, what you want is good speed. You want to collect a micro image for every position of your excitation beam, and this can be in the microsecond range. So you need, let's say, megahertz frame rate, which you don't have with an EMCCD. And also, if you want to combine it with fluorescence lifetime, like we do, then you need to be able to tag every photon with, let's say, picosecond range temporal resolution, which is also something that an EMCCD cannot give you. So especially in this context, I think SPAD array detectors are very promising, and they're already used a lot every day, more and more, because of these reasons. So I think those are the main advantages of SPAD array detectors.
Okay. Another thing that I thought, what do you think that needs to be done for SPAD array detector suitable for single molecule imaging?
Yeah, so like I already mentioned in my talk, there are some limitations with SPAD array detectors. For example, every pixel has a certain dark count rate, which can be in the order of 100 counts per second or even 1000 counts per second. And you can solve this partially by cooling the detector down. But of course, it will always be more for more pixels than for a single pixel. So this is for sure something that will be that could be a limitation. Also, we see that, for example, the detector that we have, the 5x5 detector that I showed you today, has one bad pixel, a hot pixel, which has a significantly higher dark count rate than most of the other pixels. And so in order to see the single molecules, we have to turn this pixel off, because otherwise there is too much noise and we don't see this. So this is a limitation for sure. But again, the technology of SPAD array detectors is developing rapidly, and newer generations for sure will solve this problem. So this is one aspect. And then, like I already said, you have this limitation of the fill factor. So you have the pixels that have a certain space in between them, that is that space. And if a photon arrives there, then you don't detect it. So in the old generation of detectors, the fill factor was about 50%. So it means that 50% of the photons are just hitting the dead space of the detector and are not detected. And this was a problem, of course. But then in the newer generation, they use this micro lens array. So you have a micro lens in front of every pixel. And in this way, you can increase the fill factor up to more than 80%. So also this is already a lot better than the old generation. So there are some limitations, but I want to stress again that I think this is very promising, because newer generation detectors are appearing regularly, and they are much better every day. So I'm pretty sure that we will have some results on ISM flux also soon.
Right. Okay. So anyone else want to ask? Okay. We have a question from online. So I just read it through. So the question says that is it possible? It is possible to build bigger size detector instead of 5x5, like 512 by 512.
Yeah, that's a good question. It is possible, and there are labs that do this. The problem is not so much building a big detector with many pixels, but for example, if you have 512 by 512 pixels, you have too much data. You cannot transfer the data. You cannot store the data anymore in the way that we do it. So, for example, if you want to do single photon time tagging, you need to have a time tag to every photon that arrives in every pixel of the detector. And this is a lot of data already for a 5x5 or a 7x7 array detector. This is challenging, let's say. So if you have a 512 by 512 array detector, which is possible, you can have a SPAD array detector with 512 by 512 elements. But then you have to analyze the data in a different way. So typically, if you want to use this type of detector for fluorescence lifetime, for example, you cannot time tag every photon anymore and store that information. But instead, what you do is you build the histograms already on the low level, on the detector level, and then you send the histograms basically to the computer. So it is possible to have large array detectors, but then at the cost of temporal information.
Okay, we have one more question that says that, well, hold on. What is the step size of scan in space and time domain?
The temporal resolution of the detector is around 100 picoseconds. So we cannot really talk anymore about the step size because every pixel of the detector acts as an independent detector. So a photon hits a pixel, and then let's say within 100 picoseconds or with 100 picosecond resolution, the signal is detected. And at the same time, the other pixels remain active for other photons. So yeah, let's say that the temporal resolution is around 100 picoseconds in time. And then for space, it depends on the technique that you're doing. So if you scan, you can choose the pixel size that you want. Typically, you choose it to be around Nyquist or below Nyquist. So you can do 50 nanometers, 100 nanometers pixel size, scan step size, I mean. But it's something you can freely choose. Like in a normal confocal microscope, you choose the field of view that you want to scan, and you choose the number of pixels that you want to have, and then you automatically split it into the step size that you want. So it's something that you can arbitrarily choose, basically.
Yeah, Eli, I have a thought about this. Can SPAD be combined? Can SPAD be combined with intensifier to improve its performance? Do you think something like that is in your mind, or if people are trying out?
Combined with what, sorry?
Intensifier.
I'm not familiar. I'm not familiar with this.
Yeah, you see, you know ICCD camera, right?
Yes.
Intensified CCD camera. So there is an intensifier in that.
Ah, okay. But we already have single photon sensitivity with a SPAD array detector. So
yeah. Can we combine it to make it better? Like, this is the point.
That could be. I haven't thought about this yet. I'm not familiar with this, so okay. I cannot answer this question.
Okay. But anyway, Eli, it was a great talk, and we can see some of the technologically advanced detectors and the application. And once again, I thank you, Ali. Thank you for making your time. So
thank you very much for the invitation.
Good. Take care of yourself, Ali. Okay.
Thank you very much. You too.